All right.
Professor, when can we, where is it written our TAs? Because I just checked the homework and I think I'm gonna need help.
I think on the course, on the EE class, I think it should be there. I'll double check it. You should be able to find their names on EE class platform. I
Oh, I
right.
found it. Yeah, they are in Chinese. Okay, super.
Okay, yeah. Please let me know if you can find their email address. I think it should be there as well. I'll send them over again. All right. So this is like how we've said that, if we want to work with the ZP star, so this is the format of the prime P that we are looking for. But we often don't want to just work with ZP. We just want to be generic and use Z star N. This is like specifically where the group that we use for RSA. So normally we expect N to be some, for example, specifically for the RSA to be some, P, my pen slides, P times Q. So that is would be the specific group that we are looking for. And we are going, when we use the Z star N, remember that we are working with the mod N, not mod P. So I think like we gave a lot of examples and work a lot with mod P that naturally you will go with mod P. So just be careful because when we are talking about the Z star N, we are doing mod N at the end of the calculation. So there are
Just, sorry, when we do N equals P times Q, P is not a prime. Or
normally we expect for the RSA that P and Q are primes.
Okay.
It is only for RSA. Not the general rule that every group that is Z star N has to be P times Q, right? Just only for RSA, this is the case that we are looking for those N's that they have this specific pattern. But you can generate N to be anything. For example, N can be 12. 12 is like 3 times 4. It is not. 3 is a prime. 4 is not a prime. So that doesn't have to follow that path. So there are some hard problems in this groups of Z star N. Specifically, we are focusing on RSA. That's so as long as the phi of N, the size of this group is not known, there are some hard problems on this group. So as long as you don't know this thing, finding the factorization of N is hard. Finding P and Q such that P times Q is N. As long as you know phi N, we will discuss it very soon. That basically you can solve this problem, but that shouldn't be known. Determining if some element like A from Z star N, and then checking if A is in the group of quadratic residuicity of N or not. That is also a hard problem. Solving the kth root problem, just like what we have for the general case for the discrete logarithm problem, as long as k is greater than or equal to true, 2 is going to be hard. And then also finding the generators is also challenging if this if Zn itself is a cyclic. But so Z star N, there's a rule now. We are not interested about the proofs here. So as long as your N is equal to one of these values, or it has this format, so P to the power K is some integer. The only restriction is that P itself is a prime, but you can have different K. If that is the case, then the Z star N is a cyclic, and then every element is a generator. So that is the thing that you should know about it. So this drives us to this interesting page. So what we are trying to do here is trying to find out the correlation between factoring N and also computing the phi N. As a note, we know that as long as we know the prime, if N equals to, suppose n equals to p times q, that is given. Then factorization, then computing this phi n is hard because, for computing this phi n, we know that the equation is p minus 1 times q minus 1. As long as we have p and q, then we can compute the phi n. And if we don't know p and q, then we cannot compute the phi n. So what we are trying to do in this page is correlating these two problems. So you see how much they are correlated to each other. So I'm going to define factorization as a pi problem, and computing the phi n is going to be your gamma. We are going to do a bunch of reductions over here. So we are trying to do from both sides. So we want to see, if we can prove that, we can reduce pi to gamma and gamma to pi, then it means that these two problems are equally hard. So that would be very interesting properties that we can find. So this is going to be useful for us for proving the security of the RSA. So let's do one way. So the first one, it says that if factorization is given, if we have an algorithm that we can do factorization, then computing phi n is easy, right? So how do we show that one? I'm going to show that one over here. So that means that I'm reducing gamma, which is computing phi n, into the problem pi. So the gamma is that it's given that we want to compute the phi of n, right? So the problem is to phi, given n, we want to compute the phi of n. And then, so we pass just this n to the factorization. And then suppose there is an algorithm A that our input n, it would output p and q. We can do factorization. If that is the case, then it would output the p and q over here. Then we know that we can do this computation. So we can compute the phi of n, which is equals to p minus 1 times q minus 1. So if we know p and q, the word is simple, right? So it is very a standard. So what we have done is that we reduce computing the phi n to factorization, right? If somebody can solve factorization in a polynomial time, then we can use that algorithm to, of course, compute the phi n. So let's see, how about the case number 2? What about the reverse of this problem? So what we are interested to show is that if there is a way that I can relate reduce pi to gamma. So that means that on input n, I'll just pass this input to this problem of computing phi n. Now, if there is an algorithm B that on input n, it would output the phi of n. The question is that it would output phi of n. The question is that, is there a way that I can use this phi n to compute p and q? This is my question. Okay, so if somebody can compute this p and q, given n, we have some sub-algorithm B that can output phi n. The question is that, suppose given n, I can directly compute phi n. Can I use this phi n to factor n? And that is something that we are going to discuss this right up here. All right. So let me change my pen color to help later. So I want you to see a pattern over here. If I write the equation x minus p and then x minus q, I let this to be equal to 0. Then if I do the computation, I get x squared minus p plus q plus p times q, which is equal to n, is going to be 0. Right? So this is what I get. Then what I'm going to do is that I'm going to just rename some of this. So I'm going to say x to the power 2 minus, I'm going to rename p plus q to be a. Sorry, there is a x here. Ax plus n, I'm going to name it b equal to 0, just to be generic equation, right? So this is exactly what is happening over here. If you see the phi n equation, it is p minus 1 times q minus 1. And it's going to be, if I do the multiplication, I get n minus p plus q plus 1. So I'm sort of getting a pattern. So I'm going to let define a to be p plus q. And if I do so, then if I take this one, the rest of them to the other side of the equation, so I will get n. If I take this p plus q to the other side, and I would move this phi n to the other side, I said n minus phi n plus 1, so they would remain the same. So remember, we move this thing on the other side, and we move phi n inside. So we would have p plus 1 equals to n minus phi n plus 1. So I'm going to name this one to be a. And n, which is just p times q, I'm going to rename it to b. And this renaming as it is, then all I have to do is to solve this quadratic equation. Let me make it clear. Let me actually give you an example. Let's see what are we doing here.
Sorry, I think you went too fast, way too fast. I'm just lost. Can you repeat the blue part?
Yeah, I'm going to give you an example, then we will go back to see the equation. I think this is easier. So let's go with the numerical example. Suppose I choose P to be 23, and I set Q to be 11, okay? 23 is a prime, 11 is also prime. You all agree on that. So if somebody compute N, which is 23 times 11, if you do this computation, you would get 253, okay? And if you do phi n, if you compute phi n based on the equation is p minus 1 times q minus 1. So it's going to be 22 times 10 is going to be 220. Okay. So according to this equation, I'm going to call a to be n, which is a is going to be n minus, let me write it down, phi n plus 1, which is going to equal to n is 253 minus phi n is 220 plus 1, and this is going to be 34. I did the calculation before. And b is already, or n, right? b is just 253. So let me do the magic now after this. So if I define the equation, quadratic equation, x2 minus a, or a is 34x plus b, which is our b is or n, 253 equal to 0. If you solve this equation, you will end up by getting x minus 23 times x minus 11 equal to 0. And if you solve it, one of the answers is 23, the other one is 11, and we solve this equation. So I go back and see, we know that if we, we have this equation, if we let it equal to 0, we can find the roots if we get this equation. So, applying this equation, we would get x squared minus p plus q, just doing simple multiplication, x plus n equals to 0. So it looked like that we need to have p plus q, and also we need to have n.
Sorry. I feel very dumb, but I'm very sorry. I'm lost again.
Yeah.
So on the part, in the blue part where we're actually using numbers, the one that equals 11 comes from where? No,
we choose a p to be 23. We choose a q to be 11.
Yeah.
These are prime numbers.
So on the, how would I describe that? So we got a
Here.
and b. Yeah, that one. Where does that come from?
So this equation equals to 0, right? If you solve this equation, you will get x minus 23 times x minus 11 equals to 0 if you solve the roots of this equation. So let me put it this way, right? Remember that solving the quadratic equation, these two sum of this should be this one, and then you get b squared minus 4a. Remember, you compute the delta equals to b squared minus 4a, and then you do the computation, and then you find the roots. So we just found the roots of this equation, and that is the fact that, given this equation, all we have done is that we just rewrote this equation and try to compute a p plus q based on phi n, because the only information that we have is a phi n. Okay, we know somebody would give us the value of phi n, and we already know p and we already know n. So given n and phi n, you see that I can just drop them into this equation and I can solve and compute p and q. But how I can do so, the relationship comes from here. So generally, we can write this quadratic equation. And in this equation, I need to have p plus q, and also I need to know n. So n is known, but what I don't know is p plus q, right? So this is something that I need to find out. So it turns out that this is the equation for phi n. I know the value, but I don't know p and q. But let's just write this down and see what we get. If we do this multiplication, we get n, because p times q is n, and then minus p, and then minus q, and then plus 1. So I get p plus q, right? So it looked like that I can play with this equation. So from here, I go to the next line. So I can say that I can take this part on the other side and bring phi n over here. So maybe I can, instead of this, I can show it up here, so that I can say that if I rewrite this equation, p plus q equals to n minus phi n plus 1, right? This is equal to this one, this line. So therefore, I somehow find myself p plus q, even though I don't know p plus q, but I know that the value of the p plus q is n minus phi n plus 1. So we said that we assume that some algorithm B can compute this phi n. Given that, I just plug into this equation and I would be able to solve the roots of this quadratic equation, and that would give me p and q. Is that clear now? It is basically only playing with the equation and the things that we have and the things that we don't have. So all I have is n and phi of n. But in order to solve this equation, I need to find p plus q. So we need to be smart. I don't know p, I don't know q. But rewriting this equation phi n, I know that I can get p plus q is equals to n minus phi n plus 1. I know n, I know phi n, and this is just 1. So therefore, given phi n and n, I can compute p plus q, right? So then I can just replace them into this equation and then solve the equation to get the prime p and q.
And we got the quadratic one. We just got it.
The quadratic one is the secret sauce, right? So those that they attack this problem for the first time, I don't want to go to too much details, but the fact that it's is given that if you rewrite this equation this way and you solve it, you would get to know the roots. Don't ask me to go to the details of this one; that will take it so much time. But just knowing that this is the fact, so it is enough for us that we accept that this is correct. We can show with number 2 that, well, if somebody would give you phi n and you know n, then you can compute p and q. So that is all we need to know for this problem. So the details somehow matters up to understanding, but just accept the fact that this is correct. Otherwise, I have to go through a lot of details. We don't have the time for it. So all I want to show is that from from statement number 1 and statement number 2, we can show that pi and gamma are equal or equally hard, right? Because we have shown from, remember in mathematics, to show that two sides are equal, you go from one side to the other side, and then you go from, for example, right to left, and then left to right. So when you show that from both sides, you can get to the other side, you will show that those two problems are equal. Here, what we are showing is that these two problems are equally hard, equally difficult to solve. And this really closes the loop that, given any of this information, can really jeopardize the security of the RSA, that very soon we will get into this. And I hope that these small examples that I provided would really help you so far to understand a thing that, our topic. Let me see. Any other question beside that quadratic equation? All right, it seems to be good. So, it is a little bit of secret magic over here. Most of the time, reducing problems are very tricky to solve. If you happen to take a computational complexity course, you would start to connect, solving a graph to, I don't know, to some, designing a circuit, or, many different problems that they have no correlation with each other. And then there is always tricky that somehow a missing puzzle will comes in, that here is this quadratic equation that happened that if you have these things, and then you would basically be able to factor this in over here. And this is the secret sauce of this reduction. So we don't want to go into more details over here. All right. I think we had some slide that we discussed that at some points we want to generate some primes, and sometimes we want them to have a specific format. It is a very good question to ask ourselves that, well, how many primes do we have out there? What is the probability for us to find some primes? So the first thing that we want to discuss is this pi of x. So the pi of x is a set of primes that are less than or smaller than x. So let me give you an example. For example, if you compute pi of 10, the value is going to be 4, because the only prime numbers that are less than equals to 10 are 2, 3, 5, and 7, right? So we have 4. If you compute the pi of, 100, you are going to find out that you have only 25 prime numbers that are less than equal to 100. And if you do that for, let's say, 1,000, you're going to find 168. So given the percentage, we have 10 integers that you could cover, but only 4 of them are prime. So only 40% are prime. Over here, you could 100 possible integers, but you have only 25%. And over here, you could have 1,000 integers, but you have like 16.8%. So it is just reducing and reducing and reducing. So then at some point, you want to ask yourself that, well, if it really increased a lot, what is the percentage of the prime numbers that I would get when this x happened to be very huge? So for that, let's give an example. Suppose that you're working with some 1,000-bit prime p, right? So we are talking about some x that is in the order of, let's say, 2 to the power 1,000, such a big number. And then you're asking yourself, how many percentage of, what is the portion of the numbers that are less than x, but they are prime? So it looked like that we have a very nice equation to sort of bound them and find out that how many, what is the percentage of them to be prime. If you drop these values over here, for example, for example, you really choose x to be 2 to the power 1,000, and you compute this equation, ln of 2 to the power 1,000. And if you do this math, you will find out that 1% of integers that are less than x are primes, right? So this 1% is is not that negligible. It's like a a very good portion of them. So let's see actually how do we find a prime. So I think that would become makes it very easier to understand. So how to find a prime p that is less than x given integer x. Okay. So if you start with some odd value that is like large enough or whatever value that you're looking for, and we let it to be, let's say, y, and then we test this one to be prime or not. We have a primality test algorithm. If this is not, then we continue. So since this is an odd value, if we do y plus 1, we would get to an even number. We know that evens are not prime, so we just do plus 2, right? And then we would again test this one to see if it is prime or not. And then we continue. So we do y plus 4. And then we test again to see if it is prime or not. And then we continue until we find a prime. But the very good question that you can ask here is that how long are we expected to continue? In average, if we continue until the ln of x, we are, in average, we are expected, based on this equation, if we just say 1 over ln of x, if we take it very like unlikely, if you continue this until ln of x many tryards, in average, you will be able to find a prime. So given that, so you can imagine that now you can write yourself, you can imagine that how long this for loop would have to go as much as you increase this x. So there you have to try more because, you have as much as the x increases, then the likelihood of having prime numbers would reduce. You see that the probability of them are reducing. So therefore you have to, continue, your for loop has to continue for a bit longer time. And this is like the bound that you're expected to go. Of course, sometimes, you can get very unlucky and you have to continue up to there, even more than this. But normally the way that we write the algorithm is that you choose the odd number and then you continue up to your for loop up to ln of x. And if you couldn't find any prime number, then you would just drop this y and then you choose a new y and then you start this for loop again. So that is how we would proceed with this algorithm. So there would be some cases that we would want to have different primes, and we would expect our prime to have a little bit of different format. So for example, for the case number 2, we have the set pi bc of x, that again, we want to find the primes that are less than or equal to x, but we want our prime to be having this format bk plus c. P is prime, but bk or c are not prime, any integers. And if that is the case, then we can find that, so the density would reduce a little bit more because you have to multiply that to phi of b, some other equation. So looking into this and going back to this formula, so in order for you to find this prime that have this format, you can see that your for loop, the steps that you have to take in your for loop would increase significantly because you multiply this to phi of b. We are not interested here to prove where this number comes from. It's just like some facts that we just want to know them before we continue. And sometimes you see that we need to generate some primes, and you may say that at some point that, oh, it might be very difficult to find the primes. Now you know how difficult they are. In generally, they are not very difficult and they are linear to find them. Just like the previous algorithm that we discussed, sometimes we need to find some primes that they have the same format, but over here the key k has to be prime. So you remember that we have 2q plus 1. That was one of the formats. And just q is over here is k. And for this, you see that we have another factor of ln of x over b. So this is going to be a little bit more tricky and harder to find these primes. But generally, this is not a horrible for loop, and this doesn't increase much to the steps that we have to follow. So all of this, given all of this, we can find out that it is okay. Even if sometimes that we want to have safe primes because of that discrete logarithm problem, finding these prime numbers are generally not a huge issue. The portion of this sort of prime numbers with respect to their formats are high enough so that we can find them with some linear algorithm. So we don't have any problem with that. All right. So we get to some specific part. So I think this is going to be sort of tricky for you guys. I guess for many of you, this is the first time that you see polynomials and finite fields. So I'll try to give you a lot of examples again, so that to make them easier to understand, as far as I can. Let's see why do we have to show things in polynomial? So far, what we had was, some z star p or zp that we have elements 1, 2, 3, all the way to p minus 1. Okay. So we were working with the integers and we are fine. Everything works. We can create cryptographic groups. We can have groups. We can have, inverses. We can do all the things. But it turns out that in cryptography, we can go a bit beyond this, and we are working on the extended fields. That's where this whole notation comes in. And in the extended fields, what it says is that we can start to work with higher degree polynomials. So let's say I can have a polynomial, let's say x5 plus 10 x4 plus, I don't know, p minus 2 x3 plus 12, right? Where the coefficients over here are all coming from z star p. But, I can present this instead of having just one integer, which is this last value over here on the zp, I can extend them and I can have higher degree polynomials using the same zp star. So it looked like that so far, what we've been working on was just some polynomials that, when I choose the element a from z star p, I could just show them as 0 times x5 plus 0 times x4 plus 0 times x, 3 plus 0 times x2 plus 0x plus a, right? So I was basically working I could imagine that I'm working on the polynomials, but the coefficient of every of these elements used to be 0. So I just had an integer a. But so it looked like that what we were discussing so far, in short, was a special case of, all possible groups that I could have. So that's where the polynomials and the finite fields come into the game. Let me go to the definition. Then we go back and give a bit more examples. Looking into this whole definition over here, I want to go through some of the most important things. So the first one is K is talking about that the coefficients are coming from group K. So the K could be, for example, z star p. Like we can have this integer. So we can use 1 to p minus 1 as a coefficient. And then X is saying that when we are writing our polynomials, our variable is going to be X. Sometimes use Y, that doesn't really matter. And then this notation over here is saying that we have a irreducible polynomial that its coefficients are from X, from K, and then the variables are coming from X. You can imagine that when we are talking about the z star p, we have some p over here, that p was an integer, but now this p itself is another polynomial. For example, over here, this capital P is a polynomial an xn plus an minus 1 xn minus 1 all the way to a0. And all these AIs, which are the coefficients, are coming from this group K. Something to pay attention is that we call the degree of this polynomial is n, because the highest exponent x to the n is n, and then this is the highest one, and then the degree of this polynomial is n. And then we are going to show a set of all polynomials that we can represent. And of course, when we want to represent them, all the polynomials, we do modular p, which p is here is a polynomial. So if you divide all the polynomials to this polynomial p, the remainder of them would always have a degree less than n. So all these polynomials that you would end up having there would have the degree less than n. Now, given that, if you take two polynomials from this set, you can do addition and multiplication modular p. Let's see what do I mean by that. So let me give you an example. Suppose I take equation f to be p minus 2 to the power x3 plus 5x2 plus 4, okay? And then I take a g to be p minus 10 x3 plus 2x2 plus 1, okay? So the degree of this p and q, the degree of over here, so the degree of, which is the DEG, we follow with that format, of f equals to the degree of g equals to just 3, right? So the higher exponent is 3. It turns out that now we can do actually f plus g. That is going to be p minus 2 plus p minus 10 to the x3 plus 5 plus 2 x2 plus 4 plus 1. When you do this addition, we need to apply mod p over here, right? Because all these coefficients are coming from the group ZP. So these are we are going to apply mod ZP, mod p, so that to make sure that they remain in the same group. Another way that sometimes we would just represent this elements in these equations are just sometimes we don't really show their x variable. So what we are showing is that p minus 2 and then 5 and then 0 and then 4, that is a representation of this polynomial. And then for the second one, we have p minus 10. And then we have 2, and then we have 0, and then we have just 1, right? So this is the different way that we show, we represent them.
Sorry, the p that we're using as the coefficient of x3, for example, that p inside there, is it the same p that we're doing the mod on? And is that p a polynomial or is it a number?
Yeah. Thank you for pointing to that. That p is a capital P, and that p is the polynomial. So to make
which p is it?
This p is going to be this
the
p.
polynomial.
Yeah, the polynomial. Okay. I will have an example right now for this addition. I don't have an example, but let's go to the next slide. How much time do we have? Oh, okay, so we have a little bit of time. So this is an example. In AES, we basically use this example, and there I ask you to just trust me for the computation. Now you see for the inverse of Collins, this is the final fields that we use, and we did some computation. So K over here is just Z2, and we know that the Z2 has 0 and 1. These are the only coefficients we can have. P, the irreducible polynomial, is x to the 8, x4 plus x3 plus x plus 1. You see that the coefficients are either 0 or 1, right? So this is what we define as a p. And then the degree of p is 8 because the highest exponent is 8. So now if we want to show the set of polynomials in this group, because we apply the mod p, so the remainder of any equation that you take and then you compute mod p, the remainder is going to be something less than degree 8, right? So the maximum degree that they can have is this format. So the elements of this group are going to be some polynomials that they have this format, and then the degree of them is maximum 7. And any of these A7, AIs are going to be either 0 or 1. So now if I take two polynomials over here, let's say I choose two random polynomials from this group, k of x, pk of x, then I can compute f plus g mod p and also f times g mod p, just like what we did with the integers. But now we are dealing with the polynomials. Let me give you the problem statement before we go to the break time. So when we come back, for addition, this modular p is not very interesting. It's very easy to compute, but I think we want to go through an example over here. Let me define f. I can define f to be x to the 6 plus x to the 5 plus x plus 1. Is this f element of this group? Let's check. An element of this group, the coefficient should be in Z2. That means that the coefficients are either 0 or 1. Yes, they are. And then the maximum degree that they can have is 7. So this is 6. So this polynomial is indeed in this group. Now, if the GCD of this polynomial f and this overall polynomial p over here, if this GCD equals to 1, or another way, f is co-prime to p, then we can have another equation. We can have, let's say I can find, then that means that there is equation C such that C times F is going to be 1 mod this polynomial. So even for polynomials, I would have inverse. And that is, if you remember, in inverse column operation in AES, we have done this computation and we found the inverse. So this equation implies that we would have an equation C times F. There is an equation C times F plus some other equation, let's say D times P, which is going to be equal to 1 mod this polynomial P. And that implies that C is the inverse of this polynomial F that I have. Okay. So the goal now, after the break time, is to come back here that given, this polynomial, we are interested that we should be able to find the inverse of this element. So some hints. Now that we have maximum, A0 to A7, and these could be 0 or 1. Remember in substitution bytes, in AES, we had that we have 1 byte, and for that 1 byte, we said that we find their inverse and things like that. So we can imagine that 1 byte of 8 0 and 1s, we can treat those 0 and 1s as a coefficient of this equation. And when you see a value in that state, in the AES that is just 1 byte, we don't see that one as a integer or some just 8, integer with a binary representation. We see that one as the encoding of a polynomial that we can represent it. So for example, over here, x6 plus x5 plus x plus 1 is the encoding. If you want to encode this one into a binary, so I could have 0, 1. I'm sorry. It's going to be 1, 1. The bit 2 is 0. The 4 is also 0. As well, 1, 2, 3, 4, 5, 6, and 7, right? So this is the encoding. If I see this value in a byte, so this is encoding of this polynomial. So that's why, you know, you've seen that we were working with the bytes and then somehow we were doing inverse of them. And that's, I hope that it makes it clear that the byte at, you know, in the AES computation in some parts, we were treating them as polynomial. All right, let's take 10 minutes break and then we come back and then I will discuss more about this specific problem.